Excellent. All right. Thanks everybody for coming back to the session. This is session number 3 at the Keck Science meeting. This session is going to focus on observation and characterization of exoplanets, brown dwarfs, other types of companions to stars using direct imaging and spectroscopy. We have 4 exciting presentations that will be made by graduate students from around sort of the Keck family. And these are highlighting Keck's abilities for this particular science. And so we'll jump in and get started. Our first presentation is from Noah Swimmer, a graduate student at UC Santa Barbara, presenting on a discovery of a low mass companion around a nearby accelerating star with SCExAO and Keck. So take it away, Noah.
Awesome. Thank you so much. Thank you all for being here and having me. As Josh said, I'll be talking today about a Keck and SCExAO joint discovery of a low mass companion using direct imaging around the accelerating star HIP 5319. As a bit of motivation, over the past 2 or 3 decades, adaptive optics and extreme AO systems have enabled direct imaging discoveries of low mass companions, including and down to planets around nearby stars. And the majority of these have been the result of what we call blind surveys, which you basically look at a star just because it's there, and you see if you can see an exoplanet around it. And while this method is responsible for the majority of discoveries so far, the success rate is fairly low, something around a few percent around FG and K-type stars. And so we ask ourselves, how can we select these targets more effectively? And the way that we do that is by selecting targets based on the dynamics of the host star. For that, we have this wonderful tool published by Tim Brandt in 2021 called the Hipparcos-Gaia Catalog of Accelerations, which takes data from the Hipparcos and Gaia missions and allows us to measure the proper motional anomaly of stars that are seen in both surveys. And what this allows us to do is measure if there's any errant acceleration, any anomaly in that proper motion that may be due to an a previously unseen companion. And below here, we just have a few highlights that you either used the HGCA itself or dynamic selected methods, or selecting targets based on their dynamics. And so you can see we found everything from white dwarfs all the way down to planets. And what the star that I'm going to talk to you guys about today is a part of is the SCExAO survey for planets around accelerating stars. And what this is we basically have a survey going on in which we select a bunch of target stars based on their dynamics and based on this information from the HGCA. In order to improve on that success rate that we don't have in the blind surveys. And as you can see here, we have an intermediate mass brown dwarf, a very low mass brown dwarf, and we also have upcoming a planet that we found. There's a great animation here. It looks like I didn't upload it in the proper way. But the publication of this planet that was found because we targeted this star because of its dynamic will be published later this year in Science. And so we encourage you to look out for the press release for that because we think it's super great. Now that I've motivated this, I'll go on to talking about the system that we imaged. So we looked at HIP 5319, which is a nearby F star at about 43 parsecs from us. And so this is fairly favorable for potentially direct imaging a companion. And the reason that we chose this star and the reason it was a part of this survey is because we have this 12.9 sigma significance acceleration. And what that basically means is that the star is a very good candidate for having a low mass companion. It's something around 10 or tens of AU. And what we find is that we do. And you can see 4 different images of this planet taken with, or sorry, not planet, companion with 4 different instruments. that were taken from July of 2020 up until January of this year. Using Keck 2, we have the NERC2 camera in the L band and on SCExAO, also on Mauna Kea. We use the MKID exoplanet camera, Keras, which is an IFU, and Vampires, which is a visible light polarimetric imager. Just going into our characterization of this companion and why we found it interesting, I'm going to talk a little bit about its spectrum, go into the atmospheric modeling that we did with it, and finally, the dynamical mass fitting and how we fit for its orbital parameters and what we learned from this. So if we take a look at the spectrum here, you can see that it was observed twice by Keras, once by NERC2 and Vampires, and twice by MEC, although due to instrument constraints with that instrument, we were only able to get one photometry point. Although with all of these, we were able to get fairly precise photometry, which is fantastic because it allows us to compare our spectrum to those field stars from the Montreal Spectral Library. And what we find when we do this is that our companion most closely matches an M3 to M7 spectral type M dwarf. And so just keep that in mind going forward, but we'll put a pin in that for now. We then use all of our photometry points to compare to BT saddle atmospheric models. And what we find is that our best fit T effective and log G are about 3,200 Kelvin and at a log G of about 5.5. And what this means, and when we fit for the probable size and luminosity, is that this allows masses for our companion anywhere between 400 and about 1,700 Jupiter masses. Now, the high end is a little bit unreasonable. That would actually be more massive than the host star. But then if I could call to your attention, the 5 sigma contour lines, if you go down to these lower gravity, lower temperature solutions, it allows even lower mass solutions down to something around 40 Jupiter masses for the companion, which will become a little bit important later when we talk about the dynamical mass fitting. And so on that, using the relative astrometry from NERC2, Keras, and Vampires, and the code Orvara, which again is from Tim Brandt and his group at UCSB, we find that if you focus up here on the second posterior distribution in this corner plot, what you find when you fit using the out-of-the-box assumptions about the distribution of companion masses is that it gives you a secondary mass of around 30 Jupiter masses, plus about 35 minus 11. So in that fairly low mass range. But as you can hopefully see up in the top here, on the orbit solutions, we didn't actually observe a significant fraction of the star's orbit. And so the dynamics are not particularly constraining. For that reason, we wanted to make sure that we're not artificially reducing the masses that we think this planet can have. And so what we did, going back to looking at the spectral type of the companion, we now used a different prior on our mass when we fit using this MCMC code. And now we, instead of using a 1/m log normal prior, we used a Gaussian prior where the 1 sigma intervals basically matched what we would expect from an M3 to an M7 star. And what we found is that it does change the shape of our distribution, again, because our data is not especially constraining. However, we do see that if you look at the posterior distribution, we still do actually have a peak likelihood in that 40 to 60 Jupiter mass range. And so while we're not able to conclusively say that this is a low mass brown dwarf or an intermediate mass brown dwarf rather, we are able to with confidence say that it is a somewhat low mass companion. We hope that with precise radial velocity measurements of the host star, better coverage of its orbit, as well as continuing data releases from the Gaia mission, we'll be able to better constrain this and ultimately make stronger claims on the nature of this companion. And so just concluding here, and then a little bit on the future work, we find, and the reason we brought this here today, that SCExAO and Keck are able to work in sort of complementary areas to provide compelling direct imaging discoveries that can help one another out, especially with the suite of instruments that both have. And in regards to the actual interpretations of the system and what we learn about it, it's essential to have updated system measurements before you make any interpretations. And I glossed over this a bit in the talk because it was a bit much to go into, but I have a moment extra here. There was actually, the primary star was also a bit weird, and it has been previously mischaracterized as a binary. And so if you have conflicting characterizations of the host star or different properties of the system, that can also significantly change your interpretation of the companion mass. One of the main things that we stress is that when you do fit based on the dynamics of the system, different properties of the companion, such as the orbital parameters, the mass, the eccentricity, and the other ones that we fit for, you really need to be careful with the priors that you assume and what assumptions you make, because if you just, with these orbit fitting codes, pull values out of the box, they may not be these robust, good assumptions. And so you need to be very thoughtful when you make them, especially when your data is not constraining. And then the future work, going forward with this system, we hope we can improve, as I discussed previously, the mass estimates that we have here, and we can better constrain our interpretation of the companion. But we also hope that this dynamic selected target, by selecting targets based on their dynamical properties, we get more and more direct imaging detections of lower and lower mass companions. And that's all I have for you today. Thank you so much. And I'll take any questions.
Okay, thank you very much, Noah. Do we have any questions from the audience or online?
Yeah, and Josh, if you can look at the Slack and get the online people have the advantage. Online people have the advantage here because our host is online. Our chair is online. Adam, Bruce here. And repeat the question, please.
So now you have a 3,000 Kelvin object that might be around origin. What is the age of the star? It has to be pretty young to be that hot.
Yeah, so that is, if we go back here, essential to have updated system measurements. There is actually a wide range of estimated ages for the star that go anywhere from 8 megayears all the way to 2 gigayears. And so it's not particularly well constrained. We think there's been reports in the last 2 or 3 years that claim both very, very young and very, very old ages for the host star. And so we're not conclusively sure quite yet. And I suppose that goes into the future work. If we are able to better constrain that, that will also give us a better estimate on whether or not this is a very young or a very old or a moderately old system.
Curious how hard it was to tie the astrometry between SCExAO and Keck, and what your sense of which has better astrometry, and of course, in this room, the answer to be Keck.
Summarize it.
Yes, so the question was mixing and matching, I suppose, the astrometry between the two observatories a challenge, and which of them had better relative astrometry measurements. And the answer was it was somewhat instrument dependent. So for MEC, because of our because of the pixel scale on that instrument, that one had the least reliable, the least precise photometry, which was something like 10 milli-arc second error. And then for the Keras instrument and the NERC2 camera, both of those were something around 3 milli-arc seconds. And so it was comparable. Yeah.
If I could just ask a follow-on though, how well do you know which way is north at SCExAO compared to how well we know which way is north at Keck after, of course, all the Galactic Center work?
Sure. So the question is, how well do we know,
Positioning.
yeah, the position angle of the sky as our images and the cameras at SCExAO versus at Keck. So at least at SCExAO, which I'm a bit more familiar with, because MEC is the instrument that my group works with. We typically will take observations during engineering time of known binaries that have well-characterized position angles. And so we're able to, using those, calibrate the rest of our images and our instrumental rotation or offset from true north. Anyone else?
Okay.
One more hand in the back, Joshua.
Okay, thanks.
What made you originally think that the primary was the binary? What was the reason?
Yes. So the question is, why was the primary originally considered a binary? So back in the late 70s, there was a report on this. It's rotating very quickly. It has a V sin I of like 100 meters a second. For whatever reason, in this, they classified it as what's called an RS-CVN binary. That is a highly spectroscopically active binary with a period of less than 14 days and high calcium HK emission. And so they had the periodicity, and then a year or two later, there was a claim that you did have that high calcium emission. And so that was what led to this ultimate characterization of it as a binary. More recently, oh, sorry, my time is up, but more recently, they do think it is a single star, and the HGCA also believes so, but that was the original thing. Thank you so much. I'm sorry I ran out of time.
Thank you very much, Noah.